All right, today we're going to look at identifying functions. So some important definitions we've got here. We have linear functions, which is a function in which the graph of the solutions forms a straight line. Hence, the word line in linear. You'll see them in the form y equals mx plus b. Then we have continuous data versus discrete data. So continuous data can take on any value. So there's no space between data values for a given domain. Graphs are represented by solid lines. So for example, the number of ounces in a glass, because you can have decimal values of ounces. The weight of each chocolate chip. Again, you can have not just pounds, but ounces or decimal values of ounces. Versus discrete data has spaces between possible data values. So the graphs are represented by dots. So for example, the number of glasses in a cupboard or a cabinet, right? You're not gonna say, oh, I have 4.82 glasses in my cabinet. No, you have a solid whole number amount. Or the number of chocolate chips in a bag. I guess we could argue that one because you might have half a chocolate chip, right? But generally, you should be counting full chocolate chips that are in the bag, not a partial amount. So you can determine if data that models real-world situations are discrete or continuous by considering whether numbers are reasonable as part of the domain. So let's look at this first example here. A store sells assorted nuts for $5.95 per pound. So part A, write a function to represent the total cost of any number of pounds of nuts. So the cost, C, is going to equal, well, it's $5.95 per pound. So $5.95 times however many pounds P. And then we're going to complete the function table below to find the cost of 1, 2, 3, or 4 pounds of nuts. So down here, we have our domain is P. The rule is $5.95 times the number of pounds P. And then our range is whatever that cost is. So we're plugging in 1, 2, 3, 4 to calculate the cost. So here we're doing $5.95 times 1, which is $5.95. Here we're doing $5.95 times 2, which is $11.90. For 3, we're plugging in $5.95 times 3, which is $17.85. And for 4, we're plugging in $5.95 times 4, which is $23.80. So let's go ahead and graph this. Our Y is representing the total cost. Our X is representing the pounds purchased or number of pounds. And then we're not going to be able to graph this perfectly because it's hard when you have decimal values, but I'm going to try to do it as close as possible. So at 1 pound, it was about $5.95. 2 pounds, it's at about $11.90. 3 pounds, it's at about $17.85. 4 pounds is about $23.80. So before I finish this graph, I want to think about, is the function continuous or discrete? So if we're talking about the cost that you are paying for a certain amount of pounds, again, you don't have to buy exact amount of pounds. You can buy a pound and a couple ounces, right? So decimal values are allowed. So this is going to be continuous because you don't have to buy the nuts in whole number increments. Now, because of that, that means it's not going to be dots, it's going to be a line. So it's not going to be perfect because, again, we didn't have the exact points, but I'm going to try to make it as close to perfect as possible. So I'm drawing my line through, and that's going to show that even though we just plotted these exact points for whole pounds, it could fall anywhere on this line. Let's look at another example like that. A satellite cable company charges an installation fee of $50 plus an additional $35.95 per month of service. Write a function to represent the total cost of any numbers of months of service. So again, we're trying to find out what is the total cost. Well, it's $50 plus $35.95 times however many months. We're going to complete the table just like we did before. So our domain is months this time. The rule is 50 plus $35.95 per month, which should give us our range, which is the cost. We are plugging in 1, 2, 3, and 4. So 50 plus $35.95 times 1 month is going to be $85.95. For 2, 50 plus $35.95 times 2 months would give you $121.90. For 3, 50 plus $35.95 times 3 months would give you $157.85. And for 4, 50 plus $35.95 times 4 months gives you $193.80. So again, our Y is the total cost. But then here, this is the number of months for our X, or our domain. And let's go ahead and plot those. So we've got at 1 month, about $85.95. 2 months is $121.90. 3 months is $157.85. 4 months, $193.80. So now we gotta ask ourselves, is it continuous or discrete? Well, since you're paying monthly, we're not gonna pay for a month in a certain amount of days. We're just paying for the month as a whole. So this is going to be discrete. Because you can't pay for a partial month. So I'm leaving those as dots. I am not going to connect them. Now let's look at some other important terms. So we've got functions. A function is a rule, if we remember, we already have talked about that assigns each input exactly one output. Okay, that is important. Functions occur when every x value is associated with exactly one y value. Doesn't matter the reverse way, but it means every x should only have one y. Tables in ordered pairs. So if we are given a table in an ordered pair and we're trying to figure out if it is a function, to test whether or not it is the set of ordered pairs represents a function, we're going to look to see in that table of ordered pairs, does each input or x value have exactly one output or y value? versus if you have a graph and we want to see if that represents a function, it should be able to pass the vertical line test. So this means that any vertical line that is drawn on the graph should intersect the graph at exactly 1 point. And that'll make sense when we actually look at some examples. So let's first look at these. We've got tables. So we want every x to only have one y. So if I look at all my x's here, I don't have any duplicates, so that's what is important. There's not like a 2 and a 7 and a 2 and a 5. Doesn't matter that we have two of the same y values here, because all that matters is that the x only has one y, not that a y only has one x. So yes, every input has one output. Same thing here. Let's look at our x's. We've got -2, we've got 3, we've got -4, we've got -2, we've got 0. So first off, I see I have two -2's. I have a -2 with a 1 and a -2 with an 8. So that means that every x does not have one y because the x value of -2 has two y values. So no. And my reason would be -2 has two y values. Did that? Okay. Next part. Looking at graphs. So when we said we were checking this, we're looking to see, does it pass the vertical line test? So when I kind of go across vertically, is it only hitting in 1 point? Yes, this one is. There's no overlap. So my reasoning would just be yes, passes the vertical line test. For 6, as I go across, it does not pass, because like if I think about right here, it hits in 1, 2, 3 points. So my reasoning would be no, does not pass the vertical line test. And the reason for that is this means that our x value, let's say that x value right there was -3, has 1, 2, 3 different y values that it intersects with. And then last one here, if I did the vertical line all the way across, it's only going to hit in one spot. So yes, passes the vertical line test. Okay. Now let's look at equations. These ones can be a little bit harder, but we've got an equation represents a function if every input x will only result in one output y. Same idea, just can be a little bit harder to implement sometimes in the equations. So we can figure this out by substituting various input values in to see if an equation represents a function. So if I'm looking here, we have, let's say, 25 for y. We get that from 5 squared, and we get that from -5 squared, okay? So we have two of the same y values, but that does not matter. So it doesn't matter if y's are the same. So yes, each x has one y. We're not going to have an x value of 5 and we plug that in and we're going to get two different answers. Not possible. For 9, we've got y squared equals x. So let's think of this as the reverse. We're squaring y. So we have 5 squared, using the same example, just flipped around, would give us an x value of 25. And we also have -5 squared, which would give us an x value of 25. So these x values are the same. We have a same x, different y. We can't have that. There can't be two different y values that go with an x. So no, this is not a function. Every x does not have just one y. And then number 10, we've got x squared plus y squared equals 25. So again, since we've got this y squared just like we did over there, I know it's not going to work. If it was just y, it would be fine because our x squareds worked out, but that y squared tells me no, every x does not have just one y. And then last we're going to look at is linear versus nonlinear functions. So a linear function is a function that will make a straight line when it's graphed. An equation is linear if it can be written in the form y equals mx plus b, where m is our slope and b is our y-intercept. A table is linear if it shows a constant rate of change throughout the entire table. So let's look at these three examples. If we have x cubed, so negative 2 to the third power is negative 8, negative 1 to the third is negative 1, 0 to the third is 0, 1 to the third is 1, 2 to the third is 8. If I graph these, and I'm going to kind of try to connect it as best I can, we get this little squiggly looking line like this. So, although this is a function because it passes the vertical line test, is it linear? No. Okay? We can tell by the graph it doesn't form a line, and in the table, it's not a constant ratio. Let's look at number 4. If we plug in negative 4 times 1.5 is negative 6 plus 2 is negative 4. Negative 2 times 1.5 is negative 3, plus 2 is negative 1. 0 plus 2 is 2. 1.5 times 2 is 3, plus 2 is 5. 1.5 times 4 is 6, plus 2 is 8. So let's go ahead and graph. Negative 4, negative 4. Negative 2, negative 1. 0, 2. 2, 5, 4, 8. And it's kind of funky because the x and y axis have different increments, but if we connected these would form a straight line, so that would be linear. And the ratio that we have here is going to be constant here. So yes, it is linear. So x cubed, not linear. When it has just x, linear. Here, 12 over x. So if I plug in 12 divided by 1 is 12, 12 divided by 2 is 6, 12 divided by 3 is 4, 12 divided by 4 is 3, 12 divided by 6 is 2. So plot that, 112, 2, 6, 3, 4, 4, 3, 6, 2. We get a curved line, which is not linear. So the biggest difference that we notice, these are kind of the same thing, so we're just going to look at 6, is that those that were not linear had a power of x greater than 1. Or not even necessarily greater. Greater or less, we probably should say. Because that one kind of does have it less. And that is it.